Hello, and welcome to the Blue Waters webinar series. I'm Maxim Belkin with the Blue Waters project at the National Center for Supercomputing Applications at the University of Illinois, Urbana-Champaign. It is my pleasure to welcome you today to a new session in the Scientific Workflows webinar track. Today's webinar, titled Developing Interactive Parallel Workflows in Python using Parsl, will be presented by Kyle Chard. Kyle is a senior researcher and fellow in the Computational Institute at the University of Chicago and Argonne National Lab. Kyle leads the development of Parsl, the parallel scripting library, but is also involved in a number of other projects that are related to data-intensive computational approaches, scientific reproducibility, and cloud infrastructure. Before we begin, I'd like to remind everyone that you can ask questions online using YouTube live chat, as well as in our Slack channel, where we have Kyle's colleague, Yadu Babuji, who will try to answer your questions in the Slack or pass them along to Kyle. With that, thank you for joining us today, Kyle, and I'll hand it over to you.
Great. Thanks, Maxim. Thanks for the introduction. My name's Kyle Chard. I'm a researcher here at the University of Chicago and Argonne National Laboratory. I'd like to first acknowledge the team of people that have worked with me on building Parsl over the last couple of years. In particular, the first two here, Yadu Babuji, who's sitting here with me today and will help relay questions and probably answer a few questions as we go, and Anna Woodard, who have really led the development and use of Parsl in a bunch of different places. We're very open, I think, in terms of how we run this webinar today, so please feel free to ask questions as we go. Happy to answer anything, happy to go off on tangents if people want to dive deep into different areas. So very briefly, I'll just give you a quick introduction to the history of Parsl. So Parsl is a parallel scripting library in Python. It's 100% pure Python, allows you to compose scientific workflows and execute them from small scale to very large scale, from your laptop to a supercomputer like Blue Waters. Our team has developed scientific workflow systems for the past 10 plus years, most notably the Swift parallel scripting library and Swift-T, the extreme scale version of Swift, which I believe have been presented in earlier presentations in this series. And we've sort of here, we're taking that experience that we've learned over the last 10 years and we're trying to bring it to a pure Python environment. So there's no more need to learn another language in order to develop your workflows. So just briefly in terms of motivation, I understand that the first presentation in this series outlined what a scientific workflow is. But if you're attending this talk and you're sort of wondering where does Parsl fit in, I've got a few examples of cases where it might be useful to you. So the first that we hear a lot about is someone's developing a scientific application or analysis or some sort of processing workflow, which is comprised of a bunch of different processing steps. You can think of it as a sort of tree of steps that need to be stepped through in order to get the results that you want. Often these pieces that are being linked together are sort of external applications, binaries or scripts, and pieces of sort of translational logic in Python or other programming languages. So that's one area that Parsl is really useful. A second area that Parsl, I think, provides a lot of value is in this sort of interactive Jupyter-y environment where I've got this notebook, it works great on my laptop, now I want to be able to scale it up and run it on a million different samples or on a million different materials. And the final area that I think Parsl provides a lot of value is when you're working in a sort of distributed environment where you have multiple data that might be in different locations and you have processes that need to be executed in different locations. So I guess the one slide here that sort of summarizes Parsl, I guess, quite succinctly is this one. So the idea behind Parsl is to basically try and keep as close to pure Python as we can, but allow people to compose these workflows and allow people to execute different, what we call apps in parallel concurrently when there are no dependencies. So essentially how you go about building a Parsl workflow is you start with a Python script. You can annotate what we call apps, which are either a piece of Python that you see here in the right, where we're just returning hello world, or you can wrap an app around an external command line invocation. So here we're wrapping the echo command, but that could be any binary or any application that can be called through the command line. These apps, rather than returning the value straight away, they return a future to the control logic, and a future really is a proxy for a result that might not yet be available. So you can think of that as a promise from that app that when it completes its execution, it will return the result to the sort of overarching script that's running the workflow. These apps run completely concurrently, respecting data dependencies. So this provides a sort of natural parallel programming environment where you don't need to define the dependencies between applications, but Parsl can sort of work them out based on what's being passed between the applications. So if two applications are not dependent on one another, they'll go off and execute in parallel. And one big benefit of using Parsl is that Parsl scripts are completely independent of where they run. So you can write a script on your laptop, and then you can port that and run it on the cloud or on Blue Waters or another supercomputer or your campus cluster. And that allows people to sort of develop workflows at different scales and progress when they need to use bigger resources without needing to go back and rewrite their entire workflow all over again. So the idea behind Parsl is that these pure Python scripts basically get decomposed into this dynamic data flow type model. So you see there on the right an example of a Modus workflow, which is taking some Landsat images, processing them in different ways, recombining the outputs, and then producing different types of outputs here, a map and some images that show some overlay over the Earth. So essentially, Parsl looks at this, your Python script, and it creates a dynamic graph of tasks and their data dependencies, where the edges in the graph are essentially implicitly derived based on shared input-output between apps. And so this is in contrast, I think, to many other workflow systems. So one of the typical models for workflow systems is that you develop a graph, a dynamic a DAG, a directed acyclic graph that represents your workflow, and then you execute that graph. Parsl doesn't require you to sort of define that graph up front, which is why it lends itself to the sort of interactive computing modality, where you can essentially assemble this dynamic graph over time. You can add new pieces to it, new nodes. You can execute nodes in parallel over and over again. You can add edges, etc. And these dependencies just sort of happen and evolve over time. Tasks are only executed when their dependencies are met. So you don't run the risk of an app lower in the tree being executed before its input files are created. And as I said before, tasks without shared dependencies will execute in parallel. So in this example, you can see the land use and colorize apps share no dependencies, so they'll execute completely in parallel. The analyze app will execute as soon as its input data from the land use app are completed, but then the ensemble app won't be able to execute until both the analyze and colorize apps are completed or their data products are produced. So briefly, this is a picture of how Parsl sort of works when you map that sort of model onto an actual infrastructure. So we have here a sort of control Parsl script written in Python, perhaps executed in a Jupyter notebook. We have this Parsl engine under the covers that takes that script and will execute the individual pieces of it in different nodes. In this case, we have Blue Waters, we have Amazon, and we might potentially have other Exceed resources. And we also have these data servers that live off to the side, which might be Globus accessible or HTTP accessible or FTP accessible. So essentially, Parsl, as you run through this notebook, Parsl will construct, as I say, this dynamic graph where we're seeing these apps start to appear with dependencies linking them. As soon as these apps are known by Parsl, we can check to see if there are any dependencies. If there aren't, we can ship them off down to resources to execute. And when the results come back again, we can start completing the rest of the graph, knowing how things will perform, how the graph will sort of expand over time. So that's the dynamic graph sort of model. And then the subsequent tasks will be executed, of course, when their dependencies are met. So in terms of highlights for why Parsl, I think, is something that provides a lot of value. We see a few sort of trends in the community. I think Python is becoming increasingly prevalent as a scientific programming language. Jupyter notebooks and interactive computing a few years ago I noticed a lot of social scientists and people like that using notebooks to do these sort of interactive analyses. Now we're seeing high energy physicists, material scientists, biologists. People are jumping on board this sort of interactive analysis modality, and that might be sort of a function of the increasing interest in discovery science, big data science, where you sort of come at it rather than coming at a problem with a hypothesis, you're coming at it with a truckload of data and wanting to try and explore it and understand what's going on. So when we look at the sort of the way the scientific landscape's evolving, having a workflow system that's 100% Python that you can pip install in the same way I do any other Python package and be able to exploit the sort of growing ecosystem of scientific Python libraries that already exist, being able to stage Python data between your sort of control logic, workflow script, and the actual nodes that are executing it, and also to be able to leverage other pieces of the Python and science ecosystem. So the Python ecosystem being things like Jupyter Notebooks, the science ecosystem being things like Globus in terms of research data management. The second thing that I think provides a lot of value about Parsl is that it's completely independent of the execution provider and the execution model on which you're using. So when we say execution provider, we're talking about different computational resources on which the actual tasks are being executed. So this might be run locally, it might be run on the cloud like Amazon Web Services, it might be run on Blue Waters using Torque, it might be run on a machine like Argon's Theta, which uses Slurm. Even Theta doesn't use Slurm. Theta uses Cobalt, sorry. Cori uses Slurm, doesn't it? On a machine like Nurse Cori that uses Slurm, and even in grid environments using systems like Condor. And then when we say execution model and independent, there are sort of different ways of actually passing work from your control logic, your controller, down to the actual workers that are executing it. So one model, if I'm running on my laptop and I want to run things concurrently, would be to use multiple threads that will run on multiple processes at the same time. When I scale up to use, say, my campus cluster, it's more likely that threads will no longer work. So I'll need to run some sort of model that pushes the work down to the actual nodes for execution. And so for this purpose, we often use a pilot job model where we go and provision a bunch of resources. We deploy Parsl worker nodes on them using IPython Parallel. And then we can push tasks down to those worker nodes very quickly without needing to resubmit jobs and suffer any queue latency. And then the final execution model that we support is an extreme scale model, as you saw in the Swift-T presentation. And this is really for driving the largest machines. So pilot jobs, at least in our experience, work up to hundreds, maybe 1,000 nodes. If you go much beyond that, you start to suffer a lot of overheads in terms of latency and throughput. So when we move to some of these bigger machines that have thousands of nodes, we have the sort of extreme scale model, and I refer back to, again, the Swift-T presentation, which I believe is earlier in this, what do we call this? In this program, the scientific workflow track of webinars. And so the idea there is that essentially we form an MPI fabric across thousands of nodes, and that MPI fabric provides decentralized job scheduling and execution across those nodes. So the way in which we accomplish this separation of code and execution environment is through a decoupled configuration model. So you see here some Python code on the left that defines a configuration for using a pilot job model for the Midway cluster here at the University of Chicago. It uses Slurm. It submits to the Westmere queue. It uses an SSH channel to submit remotely to that queue and defines some sort of, I guess, allocation-y level information here around how many nodes we need and how many jobs we actually want to run per node. And then we also combine a second thread pool executor. So we have two executors here. We have this IPython Parallel executor, which is executed on the Midway cluster, and then we have a thread pool executor that's executed on the local machine in which the script is running. And of course, this could also be changed. So you could have Midway, you could add Blue Waters here, you could go and add Cori or another machine that's out there in the Exceed universe, or one of the national lab machines like Theta. And then when you define your script, you can optionally define which executors you would actually like to use for a particular app. By default, any app will execute on any of the executors that are defined in a round robin manner. But you can, if you have a preference to say use local thread execution for a particular app and remote execution for a much more heavyweight app, or an app that requires GPUs, or an app that requires some specialized hardware that might exist on a remote machine, then you can define that as an option in the in your Parsl script. So just to sort of highlight some of the scalability of Parsl, we've recently run a 72-hour job, or 3 24-hour jobs on Argon's Theta supercomputer, which is a roughly 10 petaflop machine. We used up here on the left, you see this is the Theta visualization showing us using 4,000 nodes, which is roughly 256,000 cores. And we're actually running a bunch of Singularity containers here to reconstruct telescope imagery as part of the LSST Dark Energy Science collaboration. So this shows that Parsl can go from sort of developing at small scale on a laptop or on a couple of nodes through to using the entire machine for a leadership class supercomputer. And then another aspect that we'll show you a little bit later in this webinar is the ability to actually drive supercomputers from Jupyter notebooks. So this is one thing that we're really excited about, and we hear a lot of requests for this sort of capability from the community. A lot of people are coming to supercomputing centers and even campus clusters and saying, I've got my Jupyter notebook and now I need to be able to run this at a much larger scale. So the benefit here is that you can bake Parsl into your notebook. You can run it locally. You can develop the notebook locally using a threaded model, and then you can scale up and execute that by connecting to Blue Waters, as I'll show you in a few minutes. We also have models here where if we're using things like Binder or Jupyter Hub, we can pass through authentication tokens to access external services like Globus to make this sort of whole ecosystem of scientific computing at scale a lot more transparent, and so a lot easier for people to actually deal without needing to know the sort of nuts and bolts of where all your data is, where your compute's running, and having to deal with it at that level. So as I mentioned there, Parsl provides transparent wide area data management. So essentially you can define a Parsl script with pointers to files that are Globus, HTTP, FTP accessible. Parsl will do the right thing with these files. So when you come to execute in a particular environment, it will download the file or upload it if you are sending an output somewhere. It'll stage that data using, for example, if it's running on Blue Waters, it'll take advantage of the DTNs, the large-scale high-performance data management capabilities, and we can also, as I say, deal with HTTP, FTP download, upload of files that go in and out of Parsl apps. So with that, I'll move on to the Parsl tutorial if no one has any questions. So my plan is to run the Parsl tutorial on Blue Waters using a Jupyter notebook. There's some great instructions on how to do this on the Blue Waters website. So if anyone's interested in following along at home, I suggest you have a look at the Blue Waters site /Python notebooks, and that explains how to set up a Jupyter notebook in the Blue Waters environment. If you're trying to follow along now, it may be easier to just follow along in the Binder environment, which will show you sort of Parsl 101 using a multi-threaded model running completely in the cloud. So you don't need to deploy any software yourself. You don't need to install Parsl. You can just click on that link and you'll be in a Jupyter notebook with all the dependencies there ready to run. When I'm running this Parsl tutorial, I'm going to do a few things. I'm first going to load the Blue Waters Python module, which gives me all my Python stack ready to run. I'm then going to install Parsl. For Blue Waters, we have an alpha release of the newest Parsl version, which will be coming out later this month. I thought it best to use the latest stuff. So for people that are watching this down the line, you should just be able to user install Parsl, and everything that I'm showing you here will be available. We'll then clone the Parsl tutorial, which includes 2 or 3 notebooks that highlight Parsl capabilities. For this Blue Waters demo, I have a special branch in this Git repository, the Blue Waters branch. So I suggest you check that out because it includes some of the Globus data management pieces and the Blue Waters configuration for you to be able to execute this. Okay, so do we have any questions before I move on to a live demo or a live tutorial? Okay. And can we see the new environment? Okay. So the first thing is I'm going to SSH into Blue Waters. I need to get my token. Okay, I should probably increase the font size here because people aren't going to be able to see this. You can see it? Do you want me to increase the size? No? Okay. I'll module load the Blue Waters Python environment. I'll pip install Parsl version 6.2 alpha 1. And then I will start a Jupyter notebook without the browser. So when you start the Jupyter notebook, it'll randomly pick a port on that login node for you to connect to, and then you need to create an SSH tunnel to be able to view it in your own browser. So let's do this. So it's telling me it's running on 10.0.0.147 on port 8834. Need to get my token again. Of course, it just changed. Okay, and you'll see when I did this SSH, I mapped that to port 999 on my local machine. Okay. I'll make this full screen. Okay, and I'll go to the Parsl tutorial that I just checked out. And we're going to go through the Parsl introduction tutorial here. So we'll open that. Okay, so for context, this is now a notebook that is running on the Blue Waters login node, where I'm going to be running my Parsl script here in this Jupyter notebook using worker nodes that I've requested from the allocation system. So I'm going to quickly run this so that we actually submit our job, because it's going to take a couple of minutes for us to get the job. And while we do that, I will show you what the Blue Waters configuration looks like. I'll get out of full screen. Let's open the Blue Waters configuration. So as I mentioned before, the code is completely separate from the actual configuration file that's used to define where we actually want to execute this. So this is the Blue Waters configuration. A few things to highlight to start with. First, the IP of where you're running. So if you're trying to run this yourself, you will need to set this IP to the login node in which you're connected to and you're running that Jupyter environment. So that should be the same as the SSH tunnel you just created. In terms of general things we've done here, we've defined a talk provider to connect to the Blue Waters scheduler. We've defined a local channel because we're actually running on the login node, so we don't need to do any SSH trickery from Parsl. You can also run Parsl in another way where you actually are firing things over an SSH tunnel to the machine. We're saying that we want to request a single node for this tutorial because we're only going to run some fairly simple applications. We're going to send one task to each of those nodes. Parsl can do scaling depending on workload. So these init, min, and max define the parameters in which you scale. You might be willing to scale your allocation to meet workload requirements. I'm setting all of this to 1, so we're not going to do any scaling in or out, as that'll just add time, and we don't really need it when we're only running single apps at a time. We're using the app run launcher with some overrides. So this is a special override that you need when submitting Python jobs to Blue Waters, and then some general PBS settings here saying that we want the debug queue and that we want to load the BWPy module before we run. And we're setting the wall time of our jobs to 30 minutes because that's the time we have available in the debug queue. Of course, if you're running a Parsl script and your wall time runs out, Parsl will actually go and resubmit a new job for you anyway. Okay, let's go back here and see if we have. We'll wait for that. Okay, so we are connected. If I can get out of full screen, let me get out of full screen and I'll show you that we're actually connected. So this is our login. So we can watch our queue stat. I have another job running just in case the debug queue was slow, but this was the most recent job we just submitted that we've submitted with a wall time of 30 minutes. We've been running for a little over a minute, almost 2 minutes now. Okay, so now we can step through the tutorial. Let me return again to full screen. Let me increase the size as much as we can. Okay, hopefully that's visible. And we'll run through this. So we're going to go through a few of the sort of highlights and capabilities of Parsl, understanding how it deals with Python and Bash apps, and we'll end it with showing you how we can run some sort of real-ish workflows that do various things that you'll probably be able to relate to in your own work. So in terms of basic imports, again, we need to import the Parsl library before we can do anything. We need to import the Parsl app decorators, which we wrap around Python functions to enable them to be executed in parallel. And we need to either define a configuration or import a configuration. So here I'm importing that config I just showed you. And that's all we really need to do to get running. I'm just printing the Parsl version here so we know that we're at the version that we need to be to run this. In terms of configuring Parsl, so Parsl uses this model of running an engine behind the scenes that goes through and looks at your dependencies and apps that can execute and fires them off to the execution environment. So the first thing we need to do is tell Parsl about the configuration we're using. So in this case, I've just loaded the Blue Waters configuration, which actually went and submitted that job to the debug queue and has gone and set up the infrastructure on the worker node that it's provisioned such that we can actually execute tasks on it now. So I'll come back to the config model towards the end and show you how we can change that to use local threads or change it to use even a local pilot job model running on a single node. So again, this should look very similar for those of you that are using the binder tutorial. The only difference here is instead of using the Blue Waters config, we'll be using either the local threads or the local IPython parallel config, which will just be running on the same node that we have provisioned. So as I mentioned in the slides, Parsl is built around this model of apps, where apps are these pieces of code, be it a Python piece of code or fragment, or a command line application that's executed externally. And these apps, to sort of tell Parsl about these apps, you need to decorate them with either a Python app decorator or a Bash app decorator. So Parsl knows how to handle the sort of input and output and execution of that app. So let's start with a very simple example where we have a Python app. So this is as simple as we get. We have a little Hello World app. All it's doing is returning Hello World to the script that's calling it. So if we run that, we've behind the scenes, Parsl's gone and looked at this app call. It said there are no dependencies because we haven't passed in any data objects to this hello call. It's then gone and serialized the function, the return hello world. It serialized the input args. There aren't any in this case. It shipped it off to the worker node to execute, and then it's done the reverse. It serialized the outputs and things coming back again, and then in your script you can basically get the resulting string that comes back. So in terms of how is this different than a standard Python script, the only difference here is that one, we've had to wrap the function with this Python app decorator, and two, as I mentioned in the slides, the result of the call is no longer just a string. It's actually a future with a promise to give me that string in the future. So if I just printed hello here, this will print the actual future. So you see there it's an app future where its state is pending. It's waiting for it to execute. And then if I want to actually get the result, I need to add the .result call to actually go and wait for that thing to come back again and unpackage it so that we can use it. So that's sort of the very basic Python app. If we start to think, well, how do I actually code these apps in practice? I would like to pass in arguments. So an example here, if I have a very simple multiply app that will multiply A and B, I want to be able to pass that in, send that down to the worker node to execute and bring it back again. So again, here I'm just going to show an example of multiplying 5 and 9 and getting the result. So again, that gives me 45. So the Python app is really good for composing a bunch of sort of Python programming logic. But in most cases, people building scientific workflows also have a slew of maybe legacy code, maybe newish code, binaries, scripts, a bunch of sort of different pieces that they need to link together in a somewhat seamless way. So the Parsl Bash app allows you essentially to wrap anything that you can invoke on the command line. So it could be a Java program, it could be a Fortran program, it could be bash script or really anything. It could be a standard system command like echo. And so again, here we have a few extra pieces than what we had with the Python app above. First, we have to wrap the command that we're actually executing is just returned from the function. So we do this so that we can actually package up that function, send it off, and bring it back again, and know how to actually handle it on the worker node. The second thing we do is we need to wrap our function with the bash app decorator, so Parsl knows, hey, I don't want to execute this Python vanilla, I actually want to execute this external application on using a bash command line argument, and I also want to track things like the standard out and standard error that might be coming back from that application. So this is important because a lot of legacy and bash applications, a lot of binary applications, they don't always produce nice files, take files in, take files out. They often require things like environment variables to be set. They often print their output to standard out. So we need a nice, easy way to capture that. So again, here, this is the most simple example. We're going to just echo hello world. I'm defining a file to capture that standard out, in this case, echo hello.standardout. And then I'm just going to call the echo hello function and wait for the result. And then the result, of course, for this will just be an exit code from this call. But the meat, what's actually being done, will be piped into the standard out file that we can then open up and see the contents. So there we go. We've actually gone and executed that hello world app, and we've written that to standard out. Well, Parsl's captured it and put it in this echo hello standard out file, and now we can read it. Okay, so that's sort of basic Parsl. In practice, I don't think you can build too many scientific apps using just sort of vanilla Python and bash apps. What you typically will want to do is actually establish these data flow type workflows where we string together either passing Python objects or passing files between apps. So what I'm going to do here is I'm going to create 3 files, hello 0, 1, 2, hello 0, 1, and 2, and just put hello in each of those files. And then we're going to look at a bash app that will concatenate those files. Okay, so that's just creating. This is just a simple piece of Python that will actually go off and create three files in the directory that the Jupyter Notebook's currently executing in. Now, if we look at actually a more sophisticated app, so in terms of being able to track the inputs and outputs, so this is important for establishing this data flow and for telling Parsl what it needs to wait for before it's telling Parsl what the dependencies are, telling Parsl it needs to wait for these files to be produced before it can actually execute the app. So this is a very simple cat app that's just going to cat the input files that we give it in this array, and then it's going to redirect the output into an output file that we give it. So this is a building block for building a data flow. So when I call this cat app, I'm going to call it with cat. I'm going to pass in 3 input files, hello 0, 1, and 2, and then I'm going to tell it the output file is all hellos. So this will hopefully go and read each of those 3 input files and then send each of the content of all 3 of them into this output file, and then we'll read the output file when it's done. So that's executed. So one way of doing this, we supply this inputs and outputs option. So inputs is really good for when we don't know how many inputs we actually have. But if we know we've got a couple of inputs, we can actually here, we can pass in 2 highs. Oh. We'll change this so it actually, oh, I clicked insert. Oh. Change this. So we'll make, of course, live coding is always dangerous, so I make no guarantees that this will actually work. Okay, so now we've changed this cat app. So instead of requiring this sort of flexibly large list of inputs, instead we're saying we know we've got 2 files we're passing in. We're passing in high 1, high 2. All we're going to do is add them to the cat command. So we're going to cat high 1 and cat high 2 and send it to the output files. Here we are passing in that high 1 is going to be hello 0 and high 2 is going to be hello 1. And then we're going to send this to the allhellos.txt file. So this should just print 2 hellos in that file. So you see there that we can create these very simple Parsl apps in much the same way, or exactly the same way we'd create any Python function. So this looks exactly like a Python function. The only thing is that this outputs parameter has sort of hidden connotations that we know those are the dependencies that are coming back that we can then pass on to other apps. Okay, any questions on any of that so far? Does this all make sense? Okay. So in terms of how Parsl establishes these workflows, as I've alluded to probably several times now, we use futures as a promise of what the result's going to be. So futures are a fairly common programming component whenever you're dealing in the sort of asynchronous, parallel, concurrent world. So we provide the sort of asynchronous behavior by returning a future as the result of an app that we can then introspect and say, well, is this future ready for us to use? And if it is ready for us to use, can we see the actual result of it? Can we see any error conditions? Can we see any output that's associated with it? So if you think about how this actually maps to the Parsl world, we have two types of futures. We have the sort of base app future, where every app that we execute returns a future. And then we also have this notion of a data future, where an app might return more than just the state of that application, but also a bunch of futures for each of the data products that it said it's going to produce. So if we have a look at a simple way of illustrating how futures work in Parsl, we're going to define a basic hello Python app, which is going to import the time library. It's going to sleep for 5 seconds and return hello world. We then, when we call it in our control logic, we can call hello and store it in this app future variable. We can check at any time if this app future is done by asking it, are you done? This is going to say no until it's actually complete. We can block on the results by using the .result call. Blocking on the results will actually hold the Python control logic until that result's ready, and it'll then print the result. And of course, now if we look at the future, we'll see that it is actually complete. So if we run this, it should tell us no, it's not ready. It should then wait 5 seconds and give us the result. So yes, it's telling us no, it's not ready yet. And then, of course, the hello world result comes back again. So when we think about this in terms of data futures, so again here, we're going to show the same type of example, but instead we're actually going to create an output file that we'll wait for. So this, instead of a Python app, is now a bash app. We're just going to use the system command sleep for 5 seconds, and then we're going to echo whatever the message is that we've passed in into an output file, and then we'll wait for it. So now when we call this, we create our future here. We store our future variable. We call the slow echo command, telling it to echo hello world. We tell it we want the output to be sent to a file called hello world.txt. We can look at the outputs here to see these are the expected outputs of the Parsl bash app, which will just be this hello world.txt file. We can then check the future to see if it's done, and of course it won't be done for 5 seconds. We can then block on the results again, as I said before, by calling the result call. Instead here of calling it on the app, we're actually calling it on each of the outputs. In this case, we only have one. And now that it's complete, we'll be able to check the data futures and the future of the app, which should both be complete. Okay, so here we're printing the outputs. We see the result of the actual app is giving us a single data future, which is pending. We're waiting for it to run. The app future is telling us it's not yet done. We waited 5 seconds. Now we're printing hello world, which was the message that has been sent to that file. And if we look again at the data futures, we see now that it's completed. It returned a file, which has been stored here in my home file system. And the app future now tells us it's done. Okay, so when you come to, so that's sort of the building blocks again for building a data flow workflow, because now what we can do is we can string together the outputs of one app into the inputs of the next app, and then we leave it completely up to Parsl to manage how to execute those components. And I should remind everyone again that all of this execution is not happening on the login node. All of this execution is actually being sent down to the worker nodes, to these the allocation that we have on the debug queue, a single node. Okay, so up until now, we've used sort of shorthand string paths in order to be able to map input files and output files. And this works well when you're dealing with a shared file system or on your local machine. But if you're dealing with a distributed environment where you might be running a Parsl workflow that's using 2 resources at the same time, say your laptop and Blue Waters, or Blue Waters and your campus cluster, we need to have a higher level construct for data so that we know where data is and we know when it needs to be moved in order to execute. So at the basis of this, we have this parcel file object, and you can think of this as essentially an abstraction really for just holding pointers to where data might be, and then for dealing with different protocols for actually moving data in and out of various places. Do we have a question?
It looks like someone is typing.
Oh.
Do we have a question?
I can't see people typing.
Okay.
We'll wait for the typing to be complete, and then we can interject with a question. So in this case, we're going to define a bash app. It's going to look very similar to our previous apps. This is a copy app, which looks exactly the same as our concatenate app before. We're going to cat the input file, input 0, and we're going to send that to an output file.
Carl has a question.
Sure.
How many nodes are pre-allocated? Just one for now.
Yes, so at the moment, this is completely based on what our configuration said. So in our Blue Waters config, we went and said we wanted 1 node per block, and we only wanted 1 block with a minimum of 1 block and a maximum of 1 block. So we use this construct of blocks to try and map when we have sort of collections of nodes for using MPI and other things. So essentially here we've gone and requested 1. We could go and say we actually want 50 by changing that, or we could go and say we want to start with 1 node per block, but we want to be able to scale from 1 block to 50 blocks depending on what the waiting workload is. So that's just a way of defining what we actually execute. So in the theta run we ran last weekend, we have this set to 4,000 nodes running these Singularity containers concurrently. Let me return back here. Did that answer the question? I'll take that as a yes. Okay, so back, we've got our bash app. It's doing a copy command. We're going to cat the input file, and we're going to send it to the output file. So here we're going to open a test file called cat in, and we're just going to write hello world to it. So this is just a setup piece. And then we're going to create these parcel file objects to be able to manage the in and out. So here we've created a parcel in file and a parcel out file, which is just the cat in.txt file, which we just created, and the cat out.txt file, which our app will create. We now call the copy function, passing in the in file, passing out the out file, and we'll just we'll wait for the result here and then print out the results. So this really shows you that these files are mostly unobtrusive. It looks much the same as our previous app. We don't need to do anything special here to say go and find the path or anything. We can just straight away open the file in much the same way we would anything else. We have this sort of open semantics here. Okay, so that prints hello world. And the power of this file model really comes when we start dealing with remote files. So in this next example, we're actually going to pass in, rather than defining a file locally using the full path on my local file system, I'm going to pass in a file that lives remotely. It's off the screen, but it's a GitHub. It's just sitting in our GitHub tutorial repo, which you can get at with HTTPS. It's completely public, so no authentication or anything required. We're going to define a sort numbers app, which is just going to open this file. It's going to look at the contents of it and then sort it in order. So you'll have to trust me. I guess you could at home go and have a look to see that this unsorted file is indeed unsorted. And we'll run that. So behind the scenes, Parsl is, again, submitting this job, this task to the worker node. It's then going out and saying, I need to grab this HTTP file, downloading it, and then it's going to process it using the functionality in the function there. So you see that the results are now a sorted file. So that's an example using HTTPS. We can also change this to FTP if we have a file that's FTP accessible. And then we can also change it to use Globus. So here we have a file that's sitting, I put the unsorted.txt file on a Globus endpoint. This is an endpoint I created a couple of days ago for this tutorial. It's just a shared Globus endpoint that anyone can access. I can probably show you. I don't remember what I called the endpoint, but while we wait for Globus to load. I'll show you after we complete this, I guess. Okay. don't know if my VM is going slowly or Globus is going slowly. Okay, we'll come back to that later. Hopefully our transfer will work. So as you see here, we're basically taking the previous code. We've got our sort numbers app already defined. We're just replacing this part of the sort numbers with this Globus file. We're going to submit that. To use Globus for the first time, you need to authenticate. Parsl will then manage your Globus refresh tokens after that point, and you won't need to do this again for the period that you're using it. So we'll copy that auth token, paste it here. So we're now authenticated with Globus. Parsl now will go off, submit the job for execution. It'll submit the Globus transfer request, wait for the transfer request to actually complete, for that file to be there, and then it'll so we have an error. Let's try that again. I'm not sure if that error came from intermittent problems with Globus. There's always the joys of a live webinar like this. You'll never believe me, but I've run this probably 100 times over the last few weeks and never seen a problem. I wonder if there is a... It does seem like we're having a Globus problem at the moment. That's unfortunate. You'll just have to trust me that this normally works when Globus is working. I would say that we probably can improve our errors coming back here from Parsl to tell us that this is a Globus problem rather than a somewhat cryptic type error that's occurring, but nevertheless. Okay, so now we'll move on. We've learned about files, we've learned about futures, we've learned about Python and Bash apps, so now we can actually start to compose some workflows. So these hopefully will look more reminiscent of things that you're actually doing in your science. So if we look at a very simple sequential workflow, and we are showing here that we can combine Python apps with Bash apps, we're going to have a function that generates a random number, and then a function that can save a message, a string, to a file. So now if we can define these apps. So this is sort of the building blocks for your Parsl workflow, and then we can define the control logic for your workflow. So here all we're doing is we're first going to create a variable to store a generated random number between 1 and 10. We're going to show the result of that random number, and then we're going to pass the message to the save function, which will then end up in the sequential output file. Okay, and just to prove that that is actually random, we're showing here a couple of different random numbers. The random number is indeed ending up in the file that we created. If we look now at trying to create a parallel workflow where we want to run something many times, here we can again take our generate function our generate app that we just defined. We'll define it again, and then we can generate 5, 10, 15 random numbers. So if we make that 15, we generate numbers between 1 and 100. We'll send these 5, well, now I've made it 15, these 15 different tasks off to execute in parallel, and then we'll collect the results in an array. So this is like a gather operation here. So we've sent that off, and we've got 15 different numbers returning. And again, I'll demonstrate that it is actually running things differently. So now combining those two previous steps where we have sequential, let's stitch together an input to an output, and then we can also fan out and run things many times in parallel. Now we'll define a parallel data flow where we have 3 apps, again, a collection of Bash and Python apps. We have a generate app, which will generate a random number and send it to a file. We have a concatenate app, which will take an arbitrary list of input files and concatenate them into a single output file. And then we have a Python app, which will add up every line in a file. So you can see what we're going to do here. We're going to create 5 different random numbers in 5 different files. We're then going to concatenate all of those 5 different random files into one single file where there's a new line for each number. And then we're going to add up all of the results of each of those random numbers. So there, we've gone and run that. We get different random numbers depending on what's going on. we can look here. We could, I guess we're a little bit short of time. We could look at each of these individual files and see that it had a different random number in it, and see that we are actually adding it up. So now if we look at an even more interesting application here, we're going to look at using a sort of Monte Carlo type model where we're going to try and compute pi using a Monte Carlo model. There's some description there of what we're doing, but essentially we're throwing dots in a box and working out how many are inside a circle, and that approximates pi. We're going to run this pi function 3 times and then average the results out to try and get something hopefully that's more accurate than any single one. So we have a single app here, a Python app that's computing an estimate for pi using this approximation technique. You can see here that we're defining a box and working out how many of the points are actually in the box. We're also defining another Python app here that will actually average the results of the points. I'm passing in the 3 individual ones. Again, I could pass in an arbitrary list of points to average if we wanted to. So here we're going to compute. This is the call to our pi function, which is off the screen here. So we're going to call this pi function 3 times and store it in A, B, C. And then we're going to pass A, B, and C to this average points Python app to actually work out the average of the 3. And of course, this average points app won't execute until these 3 futures that have been created from the Python, from the pi approximation function have completed. So this takes a little bit longer because we're actually dropping 10 to the 6 points in a box in each one of these apps, each one of these tasks, and then we're going to combine the results here. So it definitely takes a little longer.
So we have a question from Bala.
Sure.
Kyle, is it possible to resume a partially completed workflow?
Yeah, so that's a good question. I limited the number of slides I presented here to try and focus on giving a more hands-on tutorial. But yes, so we have checkpointing functionality, and we actually also have memoization functionality, so you can cache results of apps that have been executed before. So you can see how those two combine. So essentially, the idea being, if I have this big tree or DAG of work that needs to be computed, and one branch is successfully completed, but there's an error that stops one of the other branches. All of the completed tasks, if you enable it in your configuration, will be checkpointed, and the results will be stored such that when you rerun that app, we won't rerun anything that's actually completed before, but we'll only rerun the bits that have not completed, the bits where a failure managed to interrupt them. So it's a good question. We have a lot of information on our Parsl website as well that goes through functionality like elasticity and checkpointing, memoization, multi-site, more of the data management pieces, but we just don't have time, unfortunately, to go into all of that. So happy to talk more about that if people are interested. And so the final thing I wanted to show you is the ability to take your script and then execute it in different places. So what I'm going to define here is I'm going to define 2 more configurations. I'm going to define a config that uses a local thread pool executing using 8 threads. And I'm going to define, I called this config local config. And then I'm going to combine a config using a local IPython parallel, which is going to set up the whole worker controller model on my machine and execute the jobs locally. So again, I'm just saying execute, just set up a single node locally to do that. And then we can run an application. So this is the same as the previous application that's going to generate a number, several numbers, concatenate them, and sum the results. So if I first run this using my Blue Waters config, this is going to go off and actually run that workload on the worker node. I can now go up here and change this. So if I want to run that using threads, I can clear my Parsl config, load a local config, which has updated the data flow kernel, the engine inside Parsl, and then I can execute that in the same way. And of course, I can now change that to use IPP. So if this IPP was pointing at another cluster, I could immediately go and now execute that in the script in another location. So IPP takes a little while to set up because it's deploying a controller, deploying a worker, stitching them together, and then sending this app down a queue to actually get executed. So this should come back pretty quickly. There we go. Took a little while, but it came back. Okay, so in terms of tutorial, that's the basic Parsl tutorial. We also have in the tutorial GitHub repo, we have some more advanced features that will show you things like checkpointing, memoization, elasticity, and I think perhaps some more data management capabilities. We also have a Parsl workflows notebook, which really runs through a few different sort of patterns for developing workflows. So if you're interested in continuing beyond sort of Parsl 101, feel free to run these. They should run, they do run on the Binder environment, so you can just spin that up in Binder. Again, no need to install anything locally. So I'll just briefly go back to our slides and summarize. So I guess one question we always get when we're presenting Parsl is, where is it being used? How's it being used? So Parsl is being used in a bunch of different places and a bunch of different machines. We're using it in several campus clusters. We're using it at national labs and on Exceed machines. We're doing various things. We're doing a lot of machine learning, natural language processing, computing. Machine learning example is researchers at UIUC that are using Parsl to predict the stopping power of electrons through materials. We have a bunch of examples in bio using Parsl to do genome analyses. We're working with the LSST desk group to do a variety of different workflows, from sort of very large scale production runs, such as the one we just did on Theta, to much smaller user-oriented runs. We're doing various things with the APS here at Argonne around most often material science, computing simulations and post-processing analyses that are done there. So there's some information on the Parsl website that outlines some of the users of Parsl at the moment that potentially, if you are in the same fields, there might be some pieces that you could use in terms of Parsl apps that wrap, say, AMBER molecular dynamics simulation software or other types of codes. So just to quickly summarize, Parsl really has taken this great history of the Swift parallel scripting library and brought it to Python. The benefits here are that there's absolutely no porting of existing scripts to other languages. Essentially, you can take your vanilla Python script, add a few decorators, and you should be able to run in parallel on arbitrarily large machines from your laptop to clouds to supercomputers. We support both Python and external applications. We use this dynamic DAG model in which the DAG is created over time rather than needing to sort of pre-compile and build a DAG and then send it for execution as another step. So that gives you a lot of flexibility around how you run Parsl workflows. We build this implicit and dynamic data flow from data dependencies, so there's no need for you to manage any of those data dependencies. Parsl sort of works it out as you go, and we're able to handle sort of remote data, stage it automatically for you, string together things in a somewhat seamless way. So as I mentioned, we've already applied it to several sort of many task and HPC, HTC application domains. We've used it on many clusters and supercomputers. We have configs available for a good number of machines. Again, that's on the Parsl webpage in the documentation, at least probably a dozen machines roughly. We're increasingly integrating with the growing SciPy and scientific computing ecosystem through things like Jupyter, Globus, etc. And so the takeaway here is that these sort of data flow models, developing these scientific workflows using these implicitly parallel data flow models is productive. It's easy for researchers to develop and very easy to execute them on systems of many scales, from sort of very small local deployment to then scale it up to run on much larger machines. So that's all I've got. If anyone's got questions, I'm happy to answer them. I'll quickly point out the Parsl webpage and our Parsl Slack channel, which is the best way to get sort of instant feedback or any questions you might have.
So Carlo asks, is there any value in adding support for visualizing the workflow?
Yes, so that's a good question. So definitely. So we've got a couple of initiatives going there. So we had a prototype that we built in Jupyter to visualize the workflow in the Jupyter environment, and that was nice. But we decided that it would be better to build a more standalone visualization interface. So we're building something that works for if you're running in Jupyter, if you're running in Python shells or however else you like to actually run your notebook. The status of that is we have all the monitoring set up, so we can record both Parsl level monitoring and also worker level monitoring around resource usage. We have a database that we're able to push that into, and we have a prototype web interface that reads from that database. I would expect timeline on that is probably in the next month or two. We should have a first version out that will allow people to sort of drill down and look at their workflows that have run, detect problems, look at resource usage, etc.
Follow-up question. How do we follow that progress?
How do we follow that progress? So we have some Git issues that I think are fairly active. I don't know. Yadu can, if you ask us in the Parsl Slack channel or shoot me an email, I can send you the Git issues that we're tracking it on, and we're always looking for early adopters. So if this is something that you really want, please come and thumbs up the issue, add your thoughts on what you'd really like to see. We'd love to know like what the views are, because at the moment we're basing those views on probably 3 or 4 users that have real requirements, from sort of production level runs to sort of smaller scale usage of Parsl even locally. So yeah, any input you have, we'd love to receive it.
I think the Slack channel is probably where the most activity happens.
Yeah, there's even so our Slack channel we sort of break off. We have various channels, and it's a Slack team, isn't it? Various channels in the Slack team that actually are talking specifically about monitoring and about visualization stuff. So that would be the best way to probably go and give your input.
So Mikola asks, can you prioritize tasks in a workflow that is affect the order of execution, providing data dependencies are satisfied?
Can you, okay, so I think everyone can hear Yadu there, but the question is, can you prioritize tasks within the workflow? And the answer is, at the moment, not yet. So again, if that's functionality that you see as important, we'd love to have a Git issue. So if you could send me an email sort of describing how you would like to see that done, and we can certainly create an issue and do that. At the moment, we're focused mostly on trying to sort of map individual apps to computational resources. So things that need GPUs or things that need specialized hardware, things that need to run in particular places. So we're focused on that rather than prioritization, but prioritization I can definitely see as an important thing for us to provide. And I should say that Parsl is funded by a bunch of different places here. Most notably, we have an NSF SI2 award, which should be running for the next couple of years. So we're going to be really pushing on Parsl development over the next couple of years. And now's a very opportune time. If you have things that you would really like to see in Parsl, please shoot us an email, ping us on Slack, or create a Git issue and let us know what you would like to see, and we can try and push it in there as soon as we can. Are there any other questions?
Thank you very much, Kyle. While we don't have any more questions on YouTube channel, I think I'll ask a couple of questions myself. Sure. That I drafted. So first of all, is it possible to use multiple compute resources and data providers in a single Parsl workflow? Because this is uncommon for a research group to have access to multiple computational resources, and frequently all they care is just get the results.
So you're saying it's not common for researchers to have multiple computational resources, or is common? Because I would say we see it is very common that researchers have multiple computational resources.
Yes, exactly. Yes. So multiple.
Yes, so that's one of the, so Parsl has this multi-site support that allows you essentially to submit jobs within the same workflow to different computational resources. And we have a few people doing that, mostly between the campus and supercomputing resources. So yes, that's 100% possible. In terms of data resources, what do you mean by multiple data resources? You mean they have different, say, Globus accessible repositories, or they want to use data from their laptop and stuff from a repository online or from another supercomputing center or something?
An example would be a complex workflow where one simulation finishes on one resource and provides data for the next simulation, which might be executed on a different resource.
Okay, so at present we don't have a model yet that allows us to directly exchange data between two different sites. But what we can do is we can exchange data individually between those sites. So with Globus, assuming that those two resources are actually set up, we could allow you to, you could compose a Parsl script that basically would move the output from one resource to the other. But we don't have So it wouldn't be completely integrated in Parsl yet. It's in our roadmap to have that integration to make that completely seamless. But at the moment, you would need to know of the two resources you would need to basically create Globus files for each one of them to tee up that transfer, if that makes sense. So at the moment, the Globus support really is one of the limitations of the Globus support for us is that we haven't yet extended that to work with multi-site computational resources. It works with individual resources, so it can stage data into a resource and it can stage data out of a resource. So you see what I mean? So if we had two resources, we can stage data in and out of those two resources, but we can't implicitly exchange data between those two resources. But that certainly is on the roadmap. Probably, I don't want to estimate a timeline on that, but it's fairly high priority for us to try and make that seamless and transparent.
So I see Amazon logo. I assume that Parsl works with Amazon Cloud?
Yeah, so we've done a bunch of Parsl work on Amazon. We have a lot of researchers using Parsl to basically dynamically provision cloud instances and then execute on them. We've used it in a couple of things. We've used it for biomedical analyses, genome analyses. We've used it for text processing, where I think someone was basically downloading all of GitHub and processing that in parallel on Amazon. And we thank the Amazon group here for funding resources in terms of they've given us a bunch of compute time to develop and test out Parsl.
All right, so the next question is, how does Parsl handle errors? Yes, I have a lot of questions.
Yeah, you got a lot of questions. In terms of errors on the worker node, so
yes.
there's a lot of levels to that question. So Parsl will basically serialize the error. So if it's a Python exception that comes back, Parsl will serialize that exception and bring it back to the control logic and show you the error. If it's an error in an application, where it might get printed to say standard out or standard error, then we can bring back that standard error and inspect that. So we try and capture as much information as possible. In terms of the sort of contract between Parsl and the actual application that's executing, there's a number of ways it can fail. So an app could fail in terms of it actually segfaults, or it gives you an incorrect error code, or it could fail by not producing the agreed upon output files that are being created. So Parsl can handle all of those things. It'll basically bubble up. So if there's the error code, if it outputs an error code, Parsl will bubble that back to the control logic, where you'll see the app didn't complete successfully. It gave this error code. And you can introspect the future to see what that error code is, and any information. You can look at the standard error to see if what the error was caused by. And then if the file's not created, Parsl will also bubble that back up and say, well, we expected that it would create this output file, but it didn't. So that allows you as a developer to then address those problems. Does that answer your question? Errors, there's so many errors that could occur that...
Right, that answers my question, thank you. And the last question is, so you co-lead a project related to scientific reproducibility, right? And can you comment on that topic and Parsl, keeping in mind that Python doesn't have a standard and Jupyter notebooks allow out-of-order execution? Do you think Parsl solves this problem or not?
I'm certainly not in a position to comment on the reproducibility of Jupyter. I think, reproducibility in Jupyter is a dangerous subject, because you get a notebook, there's no guarantee the order in which the cells are executed, if the cells that are executed are even still in the notebook, if things have been filling the stuff out of state. So I would say Parsl does very little to help you with Jupyter reproducibility problems. What Parsl does do is it records a fairly fine-grained record of all the tasks that you've actually executed, all the apps that you've executed. And so you can get this sort of exported, provenance is maybe too strong a word, but this exported view of here are all the actual commands that I ran, here are all the input and output files that went in and out of things. So I think it's an area that is definitely interesting, that there's more work to be done there, and there are a lot of researchers working on and serializing and capturing provenance from computational workflows. And we're definitely engaged with those groups, but at the moment we haven't looked at sort of standard prov models and things for how we represent this data. We're basically logging it with the understanding that in the future we can explore these more sophisticated provenance capture models.
All right, thank you very much, Kyle, for the excellent webinar and actually a lot of hands-on exercises and activities. With that, let's switch to our final slide. So once again, let's thank Kyle for this wonderful webinar. Those of you who registered for the webinar will receive a summary of today's session with a link to the processed video and all the materials. Our upcoming webinars include Introduction to Performance Tuning with Cray Perf Tools by Galen Arnold. It will be in 2 weeks. And after that, we will have a webinar titled Introduction to NVIDIA Insight Systems, a Performance Analysis Tool by Sneha Kottapalli. With that, thank you, Kyle, and thank you all for joining us, and we'll see you again in the next webinar.